Is it on?
Did you use any laptop or?
No, just.
Because of we have some audience far away from
Yeah.
So
Oh.
I'm thinking how to help him to ask some question.
Oh, I
so
see.
let's choose solution. One is
To
provide
ask.
our laptop to some audience inside the class.
Yeah.
And he will help to ask the question. Another is provide the laptop directly here, and you can.
Up to you. Both are good for me. So up to you.
Depends on you. You are the teacher. You know.
It's okay. I mean, if you want, you can put the laptop here. I'm happy.
Yeah.
But if you want to use someone else, yeah, to be honest, both are fine for me.
Oh, all right.
So it's up to you. Whatever is convenient for you. I mean, if it's convenient to bring the laptop here, then it's okay. You can do that.
Yeah, laptop working.
Okay, then let's do that. Is there a way to decrease the volume, or it's okay? It's okay now.
Increase?
No, decrease.
Decrease.
But it's okay. Looks like it's okay now. Yeah. It's good. Okay. Hello. No. It's good. It's good. Just now there was the.
Message was left here or here, so I'm not.
Oh, I see. Okay, perfect. So I will try to give a look. Give a look every once in a while. But there is fine, maybe. Anywhere. But
audience will be here.
no, both are fine. The only thing is that, is there going to be enough battery?
Yeah.
It's going to survive? Okay. Very good. Yeah. Or maybe we can keep it there so that if you see it, you can tell. I mean, because maybe I forget. I forget to check. So. I mean, I can also check, so if it's up to you, but sometimes I will forget. Okay.
Okay, so Professor Cassini will continue the lectures, and this is going to be the last one.
Yep.
Okay, yeah.
Okay, thanks very much again, and thanks also for giving me this opportunity. So the goal of today is to finish the introduction. This will be probably for the next 20 minutes, and then talk about the new methods. So for the first part, I will try to to show some applications of what we did last week. So, and again, for now, all the work is due to Spicer. And today, I think, all the time, I will assume that X is a threefold. And again, over C. And F will always be, so even if I forget, will always be a folation of rank 2. So, corank 1. Many results seem to be true even in higher dimension, assuming the corank is equal to 1. But let me not talk about them. Okay, so the game is exactly the same game as the Minamoto program, Morris program. Namely, we want to find the goal, without being too precise for the time being, is to find a minimum model for a log pair, a folated pair F delta. So the game is exactly the same. I think everyone is familiar. You want to find some extreme array. If kf plus delta is an F, then there is nothing to do. So if not, there exists an extreme array for which is negative, and then you want to contract it if it gives a divisional contraction, or you want to flip it. So there is no difference whatsoever with Morris program. And okay, so let's start. So how to find the extreme array? So we already talked about bend and break, but of course that's not enough without the cone theorem. So let me talk about very briefly about the cone theorem. And again, this version is due to Spicer. So let's assume, besides what is written here, let's assume that F is non-decritical. Let's suppose that F delta is canonical. Then, exactly like in the cone theorem, due to Mori, Kawamata, and so on, the result is the following. You can describe the cone curves as the set given by those curves or those cycles for which kf plus delta is greater or equal than 0, and for which we don't know anything, plus the sum of some extreme array given by some curve xi, where these curves could be infinitely many, exactly like in the cone theorem. But so first of all, it's a curve, are curves. And this is not obvious, right? Because what he's saying is that the part on which is negative is generated by curves. I mean, spanned by curves. Okay, but we can say more about them. So, which are either rational, or unfortunately, there could be a case for which we don't know much, but it's not going to create any problem for the minimum of the program, or Xi is contained in singular locus of F. Singular locus of X. Okay, and sorry, if it's rational, so maybe I should just say like this, we can also bound the degree. So what does it mean? In particular, it means that, exactly like in the cone theorem due to Mori, it means that if there are infinitely many, then they accumulate on the hyperplane given by kf plus delta equal to 0. So the picture is always the same. The picture is here there is something for which we don't know anything, and this is kf plus delta greater than 0. And then kf plus delta less than 0. Far away from this hyperplane is just generated by a finite bunch of curves. And then, of course, they could accumulate on this hyperplane. Okay, let me very, very briefly. Yeah, those bounds are only for rational curves. Yeah. For these curves, we don't know much. But since we're on threefold, there are finitely many, so it's not going to be a problem. I mean, they're not going to create. There is no contradiction in terms of these pictures. Okay, so very, very briefly, let me describe the idea of the proof. And let me do exactly like what we did last week. We'll assume that kf plus delta is effective. Because this is the only interesting case. So let's suppose that R is an extreme array. Which is kf plus delta negative. Okay, so we define lambda to be, given there exists H ample, and lambda positive, such that R would be exactly the set of curves, the set of cycles on which this divisor is equal to 0. So in other words, this is the picture. At the moment, we don't know why it's convex. But besides being convex, we don't know anything about this cone. Then we take an extreme array, and somehow this would be kf plus delta plus lambda h. Okay. So clearly we have that since kf plus delta ipse effective, it follows that kf plus delta plus lambda h is big. Okay, but this means that I can take a little bit less than this amount, and this is still big, right? For epsilon smaller than 0. So it's still big. So for epsilon bigger than 0, sufficiently small. This is still big, but it's negative with respect of R. Okay, so this is exactly the same trick we applied last week. So in particular, there exists a surface S such that S times R is negative. Why? Because we just take an element inside the linear system generated by this. Okay. And now we want to apply a junction. The idea is that, of course, we can think of R to be contained in S. So we want to apply a junction. So if you remember, by a junction, what we have is that kf plus delta plus epsilon s times s. So maybe let me remind you what is this in 1 minute. Restricted to s is equal to kfs plus some q divisor theta. So let me remind you what these guys are. So epsilon s is equal to 0 if s is invariant. And it's equal to 1 if not. So this is just a number to make the formula be correct. And theta here, this theta, is just a Q effective divisor. Q divisor which is effective, in such a way that this pair is well behaved. Fs, it's either defoliation induced on S, if epsilon s is equal to 1. So in other words, if it's not invariant, then you can restrict the foliation. If S is not invariant, you can restrict the foliation to S, and you still get a foliation of corank 1 on the surface. If not, it's just equal to Ts. If it's a trivial foliation. But what does it mean? If S is equal to Ts, this in particular means that Kfs is equal to Ks, which is what we proved last time, more or less. Okay, so, and of course, thanks. Of course, because of this property, I mean, that's why we choose this particular S. What we have is that Kfs plus theta times R is less than 0. Where R now we think of it to be a ray inside S, not anymore on X. Okay, but then at this point we can use at the moment I just want to show that, actually this is all I'm going to show because we don't have much time. but I only want to show that it's spanned by a rational curve, modulo the singular locus. So the idea is that if epsilon s is equal to 0, then we use classical Kohn theorem for surfaces. To show that R is generated by a curve. Otherwise, we use foliated Kohn theorem, which of course it's easier than the Kohn theorem for trifolds for surfaces. And so now let me just give a very, very brief comment. Now we are dealing with a foliation of rank 1 on a surface. So this means a foliation of rank 1 on a surface. And for any dimension, this has been proven to hold. So for rank 1 foliation, on any dimension, it's been proven by Bogomolov and McQuillan. Of course, surfaces are very, very easy. So I think that you don't even need to use this theorem. But more general result has been proven by Bogomolov and McQuillan. So we are fine. Okay, so that's all I wanted to say about the Kohn theorem. Of course, we still need to prove a few more things, but the fact that it's generated by a curve follows from this fact. Oh, that's right. Thanks. Yes. Yes, this is very important. Actually, I was going to say it right now, exactly right now. Yeah, this is very important. This was exactly what I was going to say as an extra remark. So this is also due to Spicer. So let's suppose that F is above, F delta is above. Well, let me just work with delta equal to 0 for the time being. Then every kf negative extreme array is spanned by a rational curve tangent to the foliation. Okay, this is very important. Why? Because we want to preserve the fact that it's non-decritical. So in other words, you can expect what is coming next. The next thing that we're going to do is to contract this extreme array. So we want to create something like CR, the contraction defined by R. And if this was not true, if it's not tangent, rational does not play very much of a role. What is important at this moment is tangent. So the foliation induced on Y will be also non-decritical. So this will give a foliation Fy, which is also non-decritical. Okay, it's almost an if and only if. It's almost equivalent. So this result, although it follows from here and it follows from the proof that we saw pretty much, it's very, very important. Yeah. Okay, so that's all for now about Kohn theorem. Let me talk a little bit about contraction theorem, which is what I mentioned just now. Any question? Okay, so now we want to exactly do what we wanted to do, meaning we want to contract R. We don't have a base point free theorem yet. We will have it in about 1 hour. But for the time being, let's follow the step of the proof. So I'm not going to mention the base point free theorem, but I'm just going to mention the contraction theorem. And again, this is due to, what I'm going to say now is due to Spicer. Okay, let's suppose that R is above. Namely, it's a Kf negative extreme array. Sorry. So we define the locus of R to be the set, the union of all the curves C inside R. So we say that there exists at least one curve here. So now we take all these curves in this way. Okay, so something which is very much expected, but it's not completely obvious. I mean, it's not true if you just take any random array. Is that, so it's a result theorem, or maybe lemma. This object is closed. Really, of course, algebraic closed. I mean, Zariski closed, sorry. No. It's a risky close. No, that's very important for us. It's really closed. Yeah, a priori would be a countable union. But what we are going to that you don't need a proof for being countable union. It's just an observation. But what we want is that it's really close. Okay. The proof, the idea, I'm going to skip it. But it's always the same. As above, we want to find a suitable surface on which we can restrict R. So what does it mean? We know that this Kf negative. As usual, we can assume that Kf is set effective. So a little bit of perturbation give a big divisor which is still negative with respect to R. We take a surface inside here and we restrict there and we use some kind of induction. So the proof is very, very similar to what we saw just now. Okay, so that's the easy part. Actually, all I'm going to say here is pretty easy. So let me do the next step, which is exactly the same as Morris' program. So we distinguish three cases. Of course, this is of dimension greater or equal to 1. Because we say that it contains at least one curve, so it would be at least dimension 1. So there are three cases. Either locus of R is equal to X, or it's a surface, or it's a curve. It's easy to see that it cannot be a curve in the surface because it's associated to an extreme array. Okay, so the first case, it's also easy to check that it's equivalent to say that Kf is Z effective. It's not Z effective. So here one can prove, if you're interested, you can prove existence of modifiable space. But this is not very interesting because, again, Miyoka give a very, very strong characterization of this kind of foliation. So I'm going to, from a Minicourse program point of view, we don't care. Let's say that it's all happy. So this is the first interesting case. Okay, so in this case, one more time, Spicer proves that there exists a contraction R from X to X prime, which is a proper morphism, of course, projective morphism, which is, of course, birational. Divisorial, so such that the exception locus it's equal to the locus of R. And you can imagine the property. The property is that CR of a curve C is equal to a point if and only if C it's inside R. So it's the usual thing. You contract CR to some t, you contract the locus of R into some t lower dimension. Okay, so in this case, everything's fine. So maybe let me give a very, very brief proof. So let me call this star. And let me, because the proof, again, it's very simple. I mean, the difficult part was what we did last time, somehow. It's the junction theorem and finding the separatrix. But now we have all the tools, so this part of the proof are very easy. So the idea of star is the following. So let's suppose that this time we call S to, we always want to do the same game. We want to find a suitable surface. So let's define S to be the locus of R. Okay, so this is a surface. And as usual, we distinguish two cases. If epsilon S is equal to 1, namely if S is not invariant, then it's possible to show, and this is an easy calculation, but I'm going to skip it, then R is kx negative. Instead, if epsilon S is equal to 0, which means S is invariant, is tangent, then R is kx plus S negative. And also should say that and xs is log canonical. Okay, so these two properties, they're not difficult to check. It's just some computation using the tools we already have. So these are easy calculations. Okay, but then you see that it's very easy to conclude. We're in a threefold, everything is known on a threefold. So we do have a divisorial contraction of a surface if it's defined by a ray which is kx negative, or kx plus s negative where the pair is log canonical. Okay, so we use standard MVP. Okay, and if you want to do a little bit more than this, sorry, maybe let me say one more step first. One thing. As usual, after you contract, you get something good. So there exists f prime on x prime, where, sorry, I erase it. But remember, you had this divisorial contraction given by x to x prime. Is this one. And then such that if f is canonical, then also f prime is canonical. So what we do, of course, there cannot be infinitely many steps of this form because the Picker number drops by 1. So what we do is exactly the same as standard MP. Okay, so we can replace xf by x prime f prime. Okay, before I move to flips, let me say one more remark, and this the last remark I'm going to do about spice of work. So let's consider a special case, which is f is smooth. So if you remember, f it's almost never smooth. Foliation are never smooth. They can be canonical, but they will never be smooth. Almost never be smooth, because yeah, even if you take a fibration, there is always going to be some singularities of the fibers. So it's very hard to find a flash which is smooth. But nevertheless, let me give this remark. Then a few things happen. The first one, which is easy to check, is the dimension of the locus of R. It's always greater or equal than 2, which means the only divisorial contraction. But of course, it could be that you contract a surface and then you create singularities. But actually, this is not true. F prime, if CR from x to x prime is divisorial, then F prime is also smooth. And this follows from the classification of Mori and Collan-Mori of these sort of, some old results by Collan-Mori about classification of these sort of contractions. So what does it mean? It means that for smooth foliations, the MMP holds because you only have divisorial contraction, there are no flips. And of course, this MMP will always terminate because again, Picard number can only drop finitely many times. So, and MMP always terminates. So this is a nice remark, but as I said, it's not completely satisfactory because this property is way too strong. Okay. So from now on, I'm going to talk about what is new, what we can do now. So from now on, the assumption will be always the same, foliation of rank 3, foliation of rank 2 on a threefold, but yeah, pretty much we continue this program. So everything is joined with Spicer. Okay, so I'm going to first mention all the results, the main results, and then I will try to say what is new. So what you need to keep in mind, because I'm sure I will erase it very soon, is that one ingredient of this proof is to show that the extreme array is kx negative or kx plus s negative. So the goal is to use standard MMP. And that's what we're going to do in the new results as well. The problem, well, we'll see the problems. Okay, so the first theorem is that if the dimension of the locus of R is equal to 1, then we can flip R. Then the flip exists. So maybe I'll call it theorem 1. Theorem 2, and I will, if you're not familiar with this, I will explain later on what it means. Special termination holds. Okay, very briefly, if you never heard this word, we don't know yet if you can have an infinity sequence of flips. But we know that some special sequence of flips terminates. And so this would be good enough to prove theorem 3. Let me just say in a weak form, then later I will say a stronger form. So if Kf is big, so unfortunately we still don't know how to prove the full result, but still, in a few weeks ago, we gave a talk in Tokyo, and we couldn't prove this one, so this is very recent. Then there exists a mirror model. For F. Okay, so again, 3 is a consequence of 2. Okay, so I would like to talk about the tools. The problem is that, as usual, when you want to try to prove something new, you need to understand what is the good setup to work with. And it turns out that canonical singularity are not good enough. So we need to work with a different category. Of course, we want a category which is bigger than canonical. But as usual, so we want to work, let me just give an idea, vague idea. We want to work with pairs. F delta. Because as usual, this is a much nicer context to apply inductions on. But remember, KLT does not imply canonical. It's very strange, but we saw it in the very first lecture. KLT does not imply canonical. So canonical could have, and this is very natural, even if you assume the singularity are very, very nice, even if have as simple singularities, which is the minimum, which means, in other words, EF F0 is log smooth. In the first lecture, I gave a definition of log smooth. So being log smooth is exactly the same. If delta is equal to 0, it's exactly the same, assuming that F has simple singularities. It's not smooth. It's a strange language, but just because we want to imitate what happens for X delta. So even if F has simple singularity, they could exist, they might exist. They could be log canonical centers. So I'm going to remind you what a log canonical center is in a few minutes. So again, so KLT is not good enough. So simple singularity does not imply KLT. Okay, log canonical is also not good. Again, for similar reason as in the standard MP, log canonical is way too general. They're not even rational and so on. So we need to find a better set of singularities. And for the MMP, the standard MMP, DLT singularities are the good singularities. So we want to do something similar. So I'm going to introduce FDLT singularities. And I will show the difference with standard DLT singularities. So let's suppose, so this is a definition. Let's suppose that F delta, it's a log foliated pair. So remember, this means that the coefficients of delta are within 0 and 1, well, 0 and 1 included. And also, Kf plus delta is Q-Cartier. So in this lecture, to make my life a little bit easier, I will always assume X is Q-factorial. It's a bit of a cheat. And actually, it's a big cheat. The reason is because soon we will have to restrict to analytic neighborhood. So even if X is Q-factorial, of course, being the MMP preserves the Q-factoriality, but being Q-factorial does not imply analytic Q-factorial and so on. So it's not really true, but I will do it because we're not going to have too much time. Okay, so we say that F delta is F DLT if, so the first condition is very simple. Any component, both the conditions are very simple. Any component is not invariant, is transverse. Sorry, any component of delta is transverse to F. And 2, there exists a log resolution f from y to x such that for any e f exceptional, so let me write it first and I'll explain. We have a e f delta, the log discrepancy is greater than 1 minus epsilon e. Yeah. Okay, so here it's very, very important. If you know what DLT means, then this is not very surprising for you. But if in case you've never seen DLT, it's not arbitrary to put the existent for any. Because, let me give an example. So the example is if f delta is log smooth, well, log smooth also allows components to be tangent. So, and one holds. So we're assuming that this holds. Then automatically f delta is f DLT. So you see, delta could have coefficient equal to 1. You could have 2 lines passing through a point. And then if you blow up this point, as you can imagine, you're going to have here the equality holds. And it's still going to be log smooth. So that's why I cannot write for any. In this case, f would be the identity, as you can imagine. It's exactly like for DLT. You're not allowed to get any log solution, but you need to have one for which this is true. In general, they will be greater or equal, of course. Okay. Any question? Okay, so let me explain why this is good. So most of what I'm going to say is easy. Most of what I'm going to say now is going to be easy. So fact one, I'm not going to prove it, but the proof it's an exercise. If x to x prime is a sequence of a kf plus delta mmp, and I should have said before, and f delta is f DLT on x, then as usual we denote by f prime the foliation induced on x prime, and we denote by delta prime to be the push forward. So let me call this f star of delta. This is also f DLT. And this is necessary, right? Because if you want to prove any theorem, this one needs to be true. Otherwise, it's not going to be useful. Okay, let me remind you what is a log canonical center. Assume that E is such that this is equal to, the log discrepancy, it's equal to 1 minus epsilon E. So you see, it's different from what is written here because we're going above the log resolution. Then the center of E in X is called log canonical center for F delta. Okay, so as I said before, even if even if F delta is log smooth and delta is equal to 0, there could be log canonical centers. It's very easy to produce examples. So there is one difference. In the case of, maybe you saw this fact. In the case of DLT pairs, this is just a remark or an exercise. If X delta is a DLT pair, then you probably know that X is KLT, right? Well, assuming it's cofactorial. But this is not true for foliation. Of course, it's going to be DLT, but it's not going to be KLT. Okay? Because again, even if delta is equal to 0, there could be log canonical centers. Okay, what is true is that F would be canonical. Okay? Yeah, I guess this is what I wanted to say. Okay, then another fact, and this is very, very similar to the case of DLT pairs, is that let's suppose that F delta is F DLT, and W is a log canonical center. Then F delta is log smooth at the general point of W. Okay, this is exactly like if you replace F delta with X delta and you replace F DLT with DLT, you get exactly the same theorem. Of course, this is copying the same result as for DLT pairs. But it's also very useful. So this is similar to KLT pairs, to DLT pairs. Okay, so there's something which is similar and something which is not similar. I'm spending a little bit of time on this stuff because it's going to be important later on. So far it doesn't look very different, but on the other hand, remark, it's possible that, actually usually, well, I don't know, but it's possible that, and this is a bit of a problem, that there exist infinitely many log canonical centers. I'm going to show you two examples of F delta. This is not true for 3LT. Okay, why is this? I'm going to show an example, but why is this important? Because I'm going to prove, we're going to show special termination. Special termination says that after finitely many flips, you're going to be far away from any log canonical center. But you need to be a little bit careful because the number of log canonical centers could be infinite. So, okay, so let me give two examples. So the first one, it's a good exercise. Any tangent divisor, any invariant divisor, or any invariant hypersurface is F DLT. is a locanical center. So what does it mean? Even if the foliation is smooth, you could have infinitely many locanical centers. Why? Because, you see, suppose that is induced by a vibration. Then any vertical curve is, any vertical divisor, suppose this is a curve. Then fibers are locanical centers. Okay? So clearly there are infinitely many, smooth and so on. So this is a problem. But it's okay. There are very special cases, so it's not too bad. And example 2, it's a little bit more subtle, but also very easy. So let's suppose that F delta is log smooth on X threefold. And let's suppose that delta is equal to the sum of two surfaces, which meet in a curve C. Okay, so in particular, C is transverse. And it's easy to check that C is a locanical center. So far, it's exactly the same as DLT pairs. But the funny thing is that if you take any point of C, then this is also a locanical center. Okay, this is a very, very simple calculation if you just blow up the point P. Okay, so this follows from the fact that the log discrepancy so the exception device will be invariant, of course, because you're blowing up a point. And so the discrepancy you can compute it's equal to 2, something like that. So when you remove 2 upper surfaces, it becomes, no, it's 3. So when you remove 2 upper surfaces, it becomes 1. Okay, but anyway, it's an easy calculation. But, okay, so the point is that, one more time, you could have infinitely many locanical centers along this curve, which is not going to happen on DLT pairs. So we need to be a little bit careful. But the good thing is that this is the only problem. This is the only thing that can happen. So a fact, maybe I should call it fact 3, but it's very, very easy, quite easy to prove, is that outside the round down of delta, there exist at most finitely many log-canonical centers of codimension greater or equal than 2. So pretty much these are the 2 possible counterexamples. Either you take 2 objects of coefficient equal to 1 and you intersect, or you take hypersurfaces. But besides that, there is not going to be any log-canonical center. So this is what saves us when we prove, although it's very easy, but this is what it's one of the ingredients when we prove special termination. Okay, another fact, maybe fact 4. Which we proved, is that everything that we did before, it's also true in this context. So the Cone theorem, existence of CR for divisorial contraction, hold for these pairs. So we're not losing any of these theorem that Spicer proved for canonical foliation. We're generalizing the results, again, not just for the sake of generalizing, but because it's more natural, and everything works well. So, of course, the goal, maybe we should stop here, but the goal is to prove existence of flips in this context. Okay, maybe we take a break, and then we continue later on, yeah. Just that? Okay, so let me go to the new results. And so we already mentioned divisorial contraction exists. So the theorem, which is a generalization of one, is that if F delta is a FDLT pair, and R is a KF plus delta negative extreme array, such that the locus of R, so this is still closed, it's the same proof as Spicer's proof. This is still a closed object, but we assume it's a curve. Then, first of all, there exists the contraction of R, flipping contraction. And what is important here is that it's projective, I mean it's proper. In other words, Z is really an algebraic variety. And the second part, that's the difficult part. And the second part is that there exists a flip. Okay, so of course it's... So I'm going to leave this to the end because I would like to talk about some of the applications and so on. Then I'll try, depending on how much time we have, I will give more detail. But of course, this will be the main, this is the main theorem. Everything else, it's much more standard. Okay, so let me say some consequences. The first consequence is the base point theorem, base point free theorem. So which now we know how to prove in full generality. So let's suppose the assumption is exactly as before. Let's suppose that F delta, it's a FDLT log pair. And let's suppose that delta it's equal to A plus B. So where delta is equal to A plus B with A ample and B effective Q divisors. Maybe for simplicity, although it's not important, but actually ample is Q-Cartier, so you can assume it's Q factorial, but it's not important. Of course, A it's automatic Q-Cartier, so I'm not cheating. And let's suppose that Kf plus delta is big. Sorry, it's an F. Then Kx plus delta is semi-ample. So this is a little bit surprising because, I mean, of course we expect to be true, but if you remember, abundance is not true for foliations, even for surfaces. So we were not really sure whether to expect this to be true or not. We were really a little bit surprised to find out that this was true. So what is the difference with abundance? Well, the main difference is that you have some positivity coming from A. So let me give an idea. The idea of the proof is very, very simple, modulo what we proved before. There are some technical details, but this is the idea. Let's suppose that Kf plus delta is big. If not, we need to use some canonical bundle formula for which I will talk about later on. But let's suppose that this is true. Then by the Con theorem, and this is very standard, if we define A prime to be equal to 1/2 A, and delta prime to be equal to A prime plus B, then, okay, maybe I should say what I want first, and then I will explain what it means. Oh, sorry. First of all, something stupid, but let's suppose that not ample. Why? Because if it's ample, there is nothing to prove, right? The goal is to prove that it's semi-ample. So I can assume it's not ample. Otherwise, what I'm going to say now is not true. Then there exists R extreme array such that Kf plus delta prime times R is negative, and Kf plus delta times R is equal to 0. One more time, it wouldn't be true, of course, if this is ample, of course. Okay, so, and here we very much use the fact that A is ample. Otherwise, we're not able to apply the Con theorem. So maybe this is the main ingredient. I mean, somewhere the fact that delta is ample needs to play a very important role, because otherwise there are counterexamples. So maybe this is the part where things fall apart. But to be honest, I don't know. Okay. But this in particular implies that, you see, since Kf plus delta is big, by assumption, the locus of R, it's either a curve or a surface. So it's properly contained inside X. Sorry. Sorry. It's properly contained inside X. In other words, it's not the full object. It's not going to give. So in other words, if you remember, by main theorem plus the existence of the disorder contraction, CR, there exists the CR. The contraction of R. So what do we know about CR? And CR is birational. Of course, it's proper. Morphism. Okay, and also the Picard number is dropping, right? The Picard number of X is bigger than the Picard number of X prime. The problem to pay is that, and that's why here I didn't want to add this assumption, is that X prime is not cofactorial. But, so let me just say that, note that X prime is not cofactorial. But there exists a log pair F prime delta prime, where delta prime is equal to the push forward of delta, such that Kf prime plus delta prime is still Coulter-Cartier. Otherwise, we have no hope. And the reason is because of this. Okay, sorry, I should say this Kf plus delta is nothing but the pullback of Kf, and and Kf plus delta is equal to the pullback of Kf prime plus delta prime. Okay, so what do we do? Then we replace X and F delta by X prime and F prime delta prime. Okay, if Kf plus delta, oh, sorry, and then of course by this, I should say that Kf prime plus delta prime is still big. Okay, so we can replace it. If it's ample, then we're done. It's the pullback of an ample. The original one is a pullback of an ample, we're done. If not, we do again the same game. You need to be careful because it's not cofactorial anymore. But as I said, as long as you write it this way, it's fine because you're just removing some ample divisor. So Q-Cartier is preserved. So we replace and we repeat as above. And again, since the Picard number drops, so by finiteness of the Picard number, we will stop. This is the proof. So it's very simple in some sense, modulo what is written here. Okay, now I can talk about other applications of this theorem. So the most important one, of course, is existence of Mia models. So what is the main idea? The main idea is what we were talking about before, is special termination. So I'm not gonna give a proof because it's not very different from. This maybe I should say that. I would say after Shogurov. The reason why after Shogurov is because our proof that is a sequence of KFI plus delta I flips. I guess you can imagine. Sorry. You can imagine what Fi and delta I are. So, yeah, then after finitely many flips, so this could be, of course, if it's not infinite, this theorem is completely useless. So you should think of this to be an infinite sequence of flips, although we don't think that they exist, but let's suppose that it's an infinite sequence of these flips. Then after finitely many flips, both the flipping pin locus and the flipped locus are disjoint from any low-canonical center. Okay, let me comment a little bit on this. So we have some low-canonical center, which could be infinite. Okay? In some very special case, which we saw before, not only they're infinite, but they even cover the whole X. So of course, in this case, this theorem tells us there cannot be infinitely many flips. Okay? Because you could have infinitely many divisors which are a tangent. And then it means that after a while, you need to stop. But that's not very surprising, because these are very special foliations. But whether there are finitely many or infinitely many low-canonical centers, after a while, you always have to stop. The flipping locus will be disjoint from these bad objects or good objects, I don't know. Okay? Maybe let me give you. So, as I said, the proof is not very different from Shokurov's proof. The only difference is that you need to distinguish between transverse and tangent low-canonical centers. So this is the main difference. Maybe let me give you a very special case, which is not in Shokurov. It's not in Shokurov's paper, of course. So let me call this special case. So it's not, if this is the flip, if x to x prime is a flip, And S is a transverse low canonical center, which is a surface of dimension 2. Then the flipped curve is not contained in S. Okay, so this is one case where, again, the only reason why I do this is because it does not appear in Shokuro paper, because he really play with the fact that it's transverse. So what is the idea? The idea is that we have kf prime plus delta prime by adjunction once we restrict it to S prime. This is equal to kf prime S prime, S, plus, let me call it theta. Theta, sorry, where theta is greater than 0. And by adjunction, f prime s, comma theta is low canonical, or FDLT. We have a foliation on surface. I didn't prove this, but this is not difficult. You have a foliation on a threefold. Once you restrict it to a low canonical center, it becomes still FDLT. Okay? Yeah, I wrote that before. Everything's FDLT. Okay, so what is wrong? So by negativity, lemma, it's easy to check that the curve, how do I call it, Xi prime, Xi plus, is contained in the support of theta. Okay? But there is a problem, because as we mentioned before, Xi plus is tangent. So in other words, as a divisor inside S, epsilon of Xi plus is equal to 0. If you remember, this cannot happen. You cannot have a component which is tangent inside the support of theta. The definition of FDLT is exactly the first line was it does not contain any tangent divisor. So this cannot be the case. Okay, so it's very easy. It's not difficult. But the proof, our proof, it's a combination of Shokuro's proof and this kind of games. Okay, so what is the consequence of this theorem? So if F delta is a FDLT pair, and delta is exactly like, it's gone, but it's exactly like the base prime free theorem, A plus B, where A is sample and effective, and B is effective, then F delta emits a mirror model. Okay, here I need to be a little bit careful, because I never told you what a minimum model is. So let me define it. So this is, we are dealing with stuff which has low canonical centers. Usually, in the classic MMP, you prove this theorem for KLT pairs. Then if you want, you can generalize it. When you try to generalize it, it's possible that when you construct a minimum model, you extract low canonical center. So let me define. So there exists a Brashian morphism from X to Y. such that, well, the corresponding pair is f dlt and kf prime plus delta prime is an f. So far, there is nothing strange, right? But what is the price to pay? The price to pay is that this map might not be a birational contraction. So, meaning that it could extract some divisor. So if E is phi minus 1 exceptional, then the log discrepancy of E, of f delta, sorry, with respect of E is equal to 1 minus epsilon E. So in other words, it's a log canonical center. It defines a log canonical center. So what am I trying to say? I'm trying to say that the way we prove this is first is very standard. First, we take a log resolution, and then we run the MMP. But it's possible that we don't contract all the divisor. It's possible some of them are still surviving. But all the divisor we do not contract satisfy this property. Okay, if you read, I think Shokurov was the first one that was talking about the minimum of the program for log canonical pairs. It's exactly the same. When you have log canonical centers, you're always a little bit in trouble. Okay, because you could have log canonical center which do not come from delta, but they come from F. Okay, I'm not going to talk too much about that, but still this is as good as you can get. So what is the idea? The idea is a combination of main theorem, which is existence of flips, of course, plus, of course, we need to use the cone theorem at some point, plus take a log resolution, then run take log resolution, and run MMP with scaling. If you don't know what it means, it doesn't matter because I'm not going to talk about this. It's the same as in previous results by I don't know who. But anyway, the existence of minor models. Okay, and then termination follows from special termination. Okay, so in other words, by this theorem here. It's possible, if you run not a random MMP, but if you run a special MMP, then this theorem is enough to show that minor model exists. Okay, very, very briefly, let me say, why do we need delta to be big? The reason why we need delta to be big is exactly like in BCHM, meaning that we need to apply the cone theorem, we need to find an extreme array which is special, exactly the same as in the case for base point free theorem. When we proved the base point free theorem, we found a special extreme array. Here I think that the main reason why we need delta big, there are a few details, but one of the main reasons is because we need to apply cone theorem. So maybe I should say main theorem plus cone theorem. Okay, and this is not difficult. It's very technical, to be honest. I mean, there are a few pages, but it's not difficult. Any questions so far? Okay, so in the remaining time, I would like to talk about, I'm actually almost done. I would like to talk about some applications, and then I would like to give some ideas how to prove the main theorem. Maybe I should start a new blackboard. Okay. So if you're familiar with the standard MP, what I'm going to write now, it's very, very natural. One of the first application, which is useful for more application, is existence of FDLT modifications. This is very technical, but as usual, it's an important tool. So let me write what it means. So let's suppose that F delta is a log canonical pair. And here I really want log canonical pair. Then there exists on X, sorry. Then there exists F from Y to X. And there exists G gamma, foliated pair on Y, such that, well, exactly what you think is true, meaning that Kg plus gamma is equal to the pullback of Kf plus delta. The second property is that, of course, I don't want an isomorphism. So G gamma, it's F DLT. And third property is that all the divisor, if E is exceptional, then it's a log canonical place. So then the law discrepancy of E with respect of F delta, so exceptional for F, of course, it's equal to 1 minus epsilon E. So it's exactly what you expect to be true. And the proof is exactly the same as existence of DLT modification. So it follows immediately from oh, sorry, I forgot the main application. Sorry, but I already mentioned before. Well, let me just say it's 2, although I should have said before. This is not exactly simple, but let me write it here. So if Kf is big, then there exists a mere model. Okay, let me emphasize that we suffered quite a lot for this. What is the reason? In the usual MMP, what we do is, so let me give an idea very, very briefly. In the usual proof, what we would like to do to write Kf equal to A plus B, where this is ample and this is effective. And we can do that, right? Because Kf is big. And then we want to write delta equal to epsilon A plus epsilon B. So that Kf plus delta is equal to 1 plus epsilon, or maybe it's equivalent. Maybe epsilon is a bit confusing, sorry, but okay. It's equivalent to 1 plus epsilon Kf. Okay? So this would be the very natural approach. And this works for when you talk about standard MP. If you have Kx big, you do this game and you're done. But where is the problem? The problem is that even if you choose delta very, very small, it might not be FDLT. Why? Because the ample guy is fine, of course, but B could be invariant. So, but even if epsilon is small, F delta might not be FDLT. And why? The reason is because some components of B might be invariant. And we don't want that. This is very important because we cannot apply induction. So, yeah, so if you need to remember, if something of these lectures that you want to remember is that the invariant guys are bad. I mean, you cannot throw them in delta. That's one thing that that I hope it was clear in the last 3 lectures. So yeah, this game does not work as written this way. So actually it took us probably 1 month to solve this problem. So what do? We need to first, you see, oh, let me say first something else. And there is no way to change B, right? Because B could be contained in the stable base locus. So you have freedom to choose A, but you have no freedom whatsoever to choose B. So you cannot change B. But on the other hand, any of these component is a low-canonical center. Okay? So the idea, although there is a little bit of work to do, so the idea is to first apply special termination. So special termination tells us, after a while, after finitely many steps, you're not anymore intersecting those components of B, which are invariant. So, and the second, remove from delta the invariant components. So in other words, you replace delta here by some delta prime, where you'll be removing some components. And why I'm not cheating? The reason is because special termination tells us that whatever happens away from the bad guys. So I'm removing the bad guys because it's not going to touch anymore the flipping locus or the flipped locus. And so I'm still running MMP. I can run MMP without performing different. So there's some bit of work, actually. But still, this is the main idea. OK. This is the second application. I should say, oh, sorry, there are too many. 1, 2, 3. So there is, I'm not going to write, besides FDLT modification, there is a terminal modification, but it's exactly the same as for log pairs. So I'm going to spare that. I'm going to talk about something a little bit more interesting. So it's the canonical bundle formula, which I already mentioned before. So this is 3, I suppose. So very briefly, let me just say that, let's suppose that, one more time, F delta is a log canonical pair. And let's suppose that F from X to Y is a fibration. So in other words, it's a proper morphism with connected fibers. And such that the fibers are tangent to F. And the second property is that Kf plus delta restricted to the general fiber is equal to 0. In other words, this is true. Okay? Then there exists G gamma log canonical foliated pair on Y. So you should think of Y to be a surface or a curve, because of course the other cases are obvious, such that, well, exactly what you want is true. Kf plus delta is the pullback of Kg plus gamma. Okay, so this is very similar to the canonical bundle formula due to Kawamata, Fujimori, and so on. The proof is also very similar. Let me say that this is, if you remember, when I proved, or I gave an idea of the proof of the base point free theorem, I assumed that kf plus delta was big. If it's not big, then we use this theorem, plus a little bit of work. Okay, so the fourth application is a weak abundance. And this was conjectured to be true. The conjecture in every dimension, to be honest. But of course, we only prove it in dimension 3 by Loret, Pereira, and Touzé. So what do we prove? I'm not going to talk about the proof, but I'm just going to say the theorem. Suppose that F delta is a fluid pair such that C1 of kf plus delta is equal to 0. Then the codal dimension of kf plus delta is equal to 0. Okay, what does it mean? It means that if it's numerically equal to 0, then it's torsion. So as I said, there are many counterexamples for abundance. You can assume delta is equal to 0, for instance. There are many counterexamples for abundance, but all the counterexamples are not numerically trivial. And so this theorem makes sense. In the case of varieties, this is known to be true in any dimension by Kawamata, I think. So this is somehow generalization of Kawamata theorem. Oh, finally, the very last application, which we hope will be true, will be useful for applications, is that the last application is that FDLT, but I'm not going to talk about this, implies non-decritical. And strangely enough, we apply MMP to prove this theorem. Okay, in the last 10 minutes or a bit more, I want to give an idea of the proof of the existence of flips. So we see that the idea is very, very simple, but I will show what are the problems. So main theorem, remember, was saying that flip exists. I'm not going to write it again. But the idea is very simple. Flips exist. Okay, so if you remember, when I talk about divisorial contraction, and this was the idea of Spicer, was you want to find some surface such that, so recall, if locus of R was equal to a surface, then the idea was to find there exists maybe S, such that R is kx plus epsilon s times s negative. Of course, if epsilon s is equal to 0, this is totally useless. But okay, And then apply standard MMP. Oh, I mean, not MMP, but anyway. I guess what I mean by MMP is the classic MMP. Okay, so we want to do something similar. We still want to use standard theorems. We want to use existence of flips. I suppose we're in dimension 3, so we want to use Morris result. So let's assume that locus of R is a curve. So let me call step 1. This is the most difficult case. The other cases are not too bad, but the most difficult case is when, otherwise the proof would be, well, I will explain what is the proof in the other cases, but the most difficult case is when there exists C inside R such that C is contained in the singular locus of F. Okay, so what does it mean? The idea is that we want to find a surface, or maybe more than one surface, for which, so we would like to find delta, whatever delta is, I'm going to be more precise later on, such that such that R is kx plus delta, here x negative. Of course, delta greater than 0. So. Okay, why this is important? Because if you can do that, then you can use the usual MMP, usual existence of flips. And so we're done. So we're not reproving anything important. We're really using standard MMP. We're not giving a new proof of the standard MMP. But I will show you what is the problem. If the curve is not contained, so let me just say as a remark. If C is not contained in the singular locus of F, then we saw last time by Cano, there exists S separatrix, unique, invariant surface containing Xi. And it's easy to check that nkx plus Xi, nkx plus S, times R, let me just write it like this, is negative, or times C is negative. Okay, so we are happy. The problem is that this is true only in a analytic neighborhood of what's the name of Xi. Okay, so how do we proceed? In this case? Well, first of all, by Artin theorem, okay, I'm going to use two different theorems by Artin. This is very simple. It's about the normal bundle being, the dual of the normal bundle being ample. So there exists some kind of contraction from X to Z, contraction of Xi. But the problem is that Z is analytic, where Z is, it's an algebraic space. Okay, so we have two problems. One is that you have only Z to be an algebraic space, and the other one is that only its analytic neighborhood. But pretty much it's the same problem. So we have, you should think of it to be a threefold. No, sorry, this is a bad picture. Let me just draw a normal picture. You should think of it to be a threefold, where you have a surface S, which is only analytic, and everything is mapped to a threefold, where this curve Xi is mapped to a point. Okay, this is the contraction. Okay, now you need to do some MP in this case. But MMP in this case is not very badly behaved. You take some metal neighborhood, you work. So MMP in this case works. Namely, the resist really, even if you have, so this map is proper. This is not projective, but this map is proper. So even if this guy is not an algebraic variety, but it's an analytic variety, in other words, it's the spec of an Ensilian ring. So let me write it as. You can assume, sorry, I should have said at the very beginning, existence of flip, it's a local problem. This is a standard fact. So you can assume this is affine. But since we are taking an analytic neighborhood, we can assume we work on spec A, where A is Ensilian. In this case, MMP works. You need to prove it, but it works. Okay, but what is the problem for us? The problem for us is that it's not true that C is contained in the singular locus of F in general. So let me very briefly go to the case of surfaces. So let's think about surfaces. If you have a point P inside the singular locus of F on a surface, so we saw few examples on which there is more than one separatrix. You could have actually two. They could be two invariant surfaces, two invariant curves passing through P. So it's like this. What is the problem? So let me write it first. So similarly, if C is contained in a singular locus of F, there could be S1 and S2 separatrices such that Xi are contained in S1 and S2. What is the picture? The picture is very simple. This is Xi, and then you have two surfaces. Okay, what is the good news? The good news, it's what you hope to be true is true. Namely, Kx plus S1 plus S2 times C is negative. Even more is true. X comma S1 plus S2, I'm cheating a little bit, but it's log canonical. So this looks great, right? You have not one, but you have two surfaces, but nevertheless, you have a log canonical pair, it's three-dimensional, on which this is negative. So this is the good news. The bad news, and this is where, of course, all the problem comes, is that, and this you can construct counterexample, it's not lack of proof. You really can construct a counterexample. We can choose S1 to be analytic, which is good enough. In other words, it's defined in a neighborhood, analytic neighborhood of Xi, exactly like here. But S2 might be formal. It could be not, of course, but in a difficult case, it might be formal. What does it mean? It means that it only exists, even in the case of surfaces. I was a little bit cheating when I said there are two invariant curves. One of them could be formal. In other words, it's only existed if you take the completion of the point, of the local ring defining the point. Okay, so this is a problem. Sorry. So what is the solution? How do we want to solve it? Well, instead of working with Ancillian, we would like to work with a complete ring. But the MMP does not work for formal schemes. There are, well, I don't know if there are counterexamples, but for sure, there is no proof. Even Kawamata feedback is false in formal schemes. So running MMP on formal schemes, it's at the moment is out of reach. So I'm protecting myself. I'm not saying that it's impossible because it would be too much, but it's way beyond our capabilities to run MMP. So we need to do something by hands. Okay, so let me go to step 2. Okay, I would like to talk about it, but probably I don't have time. So the idea is that, okay, let me draw the picture. It's exactly like before, but now we don't work with A to be anymore a Ancillian local ring, but it's a complete local ring. So it's like you take formal series rather than usual stuff. Okay. So what we want to show that, let me write a vague idea, then maybe I will be more precise soon. There exists a sequence of surfaces, SIM, S1M, and S2M, containing C, such that they are really analytic. For M sufficiently large, the pair given by these two surfaces is still canonical. I mean, what was true before is still true. And Kx plus S1M plus S2M times C is negative. Okay, so, and so we can run MMP. Okay, so how do we do that? Let me give a very, very brief idea. So we know the existence of, so the idea is that there exists CR on some formal neighborhood. Well, let's do it a little before. Let me assume that Z is equal to spec of A. Okay, where A, I'm assuming that it's a local ring. What does it mean that, so with maxima ideal M? What is the maxima ideal? The maxima ideal is very simple. It's just is the ideal defined the point. What does it mean that we want to find S1M and S2M? It means that the idea is to define X of M, XM to be, well, let me just write it very vaguely. So we have X to Z, where this is spec of A. And then you have spec of A to the, okay, there are too many M, sorry about that. Okay, let's call the maximum idea A, otherwise we get crazy. Spec of A to the M. Okay, and then you have a diagram like this. So what is the formal neighborhood? The formal neighborhood is just a limit, the direct limit of all this XM. Okay, so what are these SIM? So the SIM are satisfy the property that once you restrict to xm, they're equal to si restricted to xm. Which makes sense because, remember, Si are only defined on a formal neighborhood, but this lives inside the formal neighborhood. This is the standard restriction, and this follows from the fact that on a formal neighborhood you can take the restriction on over every of these guys. Okay, we're almost done. Or at least, I guess I'm taking too much of your time, so I'm going to stop soon. So, at this point, we apply Artin's theorem. To find SIM, we need to apply Artin's theorem. So we would like to apply Artin theorem. It's a different theorem. Maybe I should call it approximation theorem. To find SIM. What is the problem? The problem is that you need to approximate two things. You need to approximate both the line bundle. So the difficulty is to approximate both the line bundle, and this follows from Artin's theorem. I mean, Artin really proved something like that. Both the sheaf, so let me call it L equal to OX of SI, the completion, where this is the formal neighborhood. Of C in X. Okay, so you have some formal neighborhood, and you have a line bundle given by SI. You know that SI exists on X tilde, so you first need to approximate L hat, and that's possible, meaning that Artin's theorem really tells you that you can find such an L. But also you need to approximate the section. The section SI corresponding to H0 of L. Sorry, here there's a I, because there's a I here. L at I. And this is not given by Artin's theorem. So it's getting very technical. I'm also running out of time. So let me just say that for this, we use a theorem by Elkick. For this, we apply a theorem by Elkick. Okay, so this part is very technical, and for me, it was very new. I never really used this stuff, so that's why we spent quite a lot of time on this proof. Okay, thanks very much. I will stop here.
Thank you very much. So, any questions?
Yeah, that's right. And also flipping formally. But only for, so we don't prove MMP or anything like that, only in this very, very special case. Namely when you have two surfaces, I mean, this kind of picture. Yeah, MMP, it's maybe something like this will give MMP, but it's a very, very special case because there is a proper morphism on the spec of something complete. So that's exactly, maybe we can push it all the way to prove MMP in this direction. But this is a very, very special condition. So proving MMP for formal schemes, it's way out of reach at the moment.
There's no question there.
Okay, thanks.
Any question? Any more questions? If not, let's end the speaker again. Thank you.
Thank you. How do you switch off? Do you know? Sorry, I mean, it's very dirty.
That's okay. I think
I don't know if it's automatic.